All right, so here we are. Maybe in some ways like the pivotal lecture of the entire class. Certainly not the hardest. That might be partial F tests. Certainly not the longest. That would be diagnostics. But oh man, I'm ruining my own dramatic moment. Um, but maybe like the most pivotal and the most important. Um, where we really finally head on tackle the idea or concept of how to build, right, the best equation. That is, right, we have a data set. The data set maybe has 5 variables, maybe 10 variables, maybe 20 variables, maybe hundreds of variables. And we as statisticians have the very difficult task of taking these 20 variables and saying, okay, of these 20 variables, how many do I need? Maybe it's 10, maybe it's 4, maybe it's 5. And which of the 10 or 4 or 5 are the important ones? And of course, I'm sorry, that in and of itself is challenging enough. But what? But not only do we have these like initial variables to deal with, but as we've talked about, we need to also consider things like interactions. We need to also consider things like dummy variables, right? Maybe how to break a categorical variable down into like these little dummy variables. We also have to consider things like polynomial terms, right? So maybe I have like all these like variables. I need to also consider the squared versions of these variables, the cubed versions of these variables. So, I mean, there's a lot going on. They say that good model building is as much of an art form as it is a science. And that makes it a very fulfilling, a very rewarding challenge. But, right, not to mince words and not to sugarcoat it, a challenge. It's not easy to do. And every data set has its own sort of different set of challenges and complexities associated with it. That said, I'm going to try to talk about some kind of broad brush techniques that we could hopefully use to at least get us started in any particular situation. Let me also say this. If you have not done the polynomial PowerPoints, then stop this and do polynomial first. So the order of this week's PowerPoints is supposed to be first polynomials and then model building. So if you're doing it out of order, not a big deal. Just go do polynomials and then come back. And sadly, you'll have to listen to me do my rambling preamble all over again. But hey, we're done. So let's move on. Yeah, so like I said, this class really takes everything that we've talked about up to this point and really brings it all together, right? Which is actually kind of cool. We're really taking everything now and we're actually going to use it in this kind of nice, like from beginning to end, this nice comprehensive process that allows us to build the quote best possible regression model for a given set of independent variables. Now, right, I have to put that word best in quotation marks because there's not a universally accepted definition of what a best regression model even means. I also want you to be aware that there's a lot of different approaches to model building. Every textbook has its own approach to model building. There's not one universally accepted way of doing it. Again, it's as much an art as it is a science. When you take Stat 507, presumably with me as your professor, I will actually give you another way of kind of going about this model building process. But we're going to start with one. It's a good way of doing it. The particular approach that we're going to talk about in this set of PowerPoints is essentially the approach advocated by our textbook. So it's consistent with our textbook, and right, to keep things consistent with our textbook, that's the way we're going to do it in this class. So our textbook lines it up as 5 steps to greatness. Step 1, specify your maximum model, your largest possible model. Step 2, specify the criteria that you're going to use for selecting a model. Step 3, specify a strategy for including or deleting, removing variables. Step 4, build that selected model. And as part of that building process, don't forget your diagnostics, right, that we talked about last week. And then finally, evaluate the reliability of your model. So the model building, I've taken this model building lecture, I've broken it into 3 pieces. The first piece is going to talk us through big picture. Steps 1, 2, and 3. Step 4 we've already talked about in previous lectures, so step 4 we're not really going to talk about. In this particular PowerPoint, I'm going to talk big picture about 1, 2, and 3. The second model building PowerPoint is going to apply steps 1, 2, and 3 to our Bears data set. And then our third PowerPoint is going to be dedicated entirely to that step 5 because it's such a critically important step that I wanted to give it its own PowerPoint. So step 1, right? Consider, right, the maximum model. What is the largest possible model that we are considering? Now here, again, we know from all our previous lectures, this is not just like the number of variables in our data set. Because we need to also consider possible interactions, we need to also consider polynomial terms. Again, this is my suggestion. You might find counter suggestions from other colleagues, from future coworkers, from different textbooks. But for this class, I'm going to recommend that unless given convincing evidence to the contrary, not to worry about anything more than pairwise interactions. That is, interactions between just 2 variables. Don't worry about 3-way or 4-way or 5-way interactions. Also, unless you have strong reasons, don't consider polynomial terms more than order 3. So, right, between the number of variables in our model, plus the number of pairwise interactions, plus the additional squared and cubic terms, that will help us kind of create our maximum model. So, what are the constraints on our maximum model? That is, like, how many variables can I put in there? Could I put 10, 20, 100, 1,000? Well, the only real constraints on the number of variables we can put in our model is that it's limited by the size of our sample. Right, so I mean the hard limit is that your sample size must be larger than k plus 1. Right, because of the MSC degrees of freedom, right? The MS degrees of freedom are essentially n minus the quantity k plus 1, right? And if you distribute that minus through, that would become n minus k minus 1. Right, which we know is the degrees of freedom for the MSE. F statistic can't have negative degrees of freedom. So that means that n must be larger than k plus 1, or to put it another way, right, k plus 1 cannot be more than our sample size. So it's, again, it's constrained by the size of our sample. So I mean, that's like the rule, like, you know, you're going to start getting like errors from your SAS program. Now, in the ideal situation would be that we want our sample size to exceed 10 times k, right? So if we were to have a sample size of 50, that would mean that maybe ideally we would just do 5 variables. Now, that's kind of like an ideal world. That's sometimes hard to make work in the actual applied workplace. And so maybe a more practical A more pragmatic rule might be to have your sample size be more than 5 times k. So in that case, if we had a sample size of 50, that's saying we can maybe get away with 10 variables. Does that make sense? So kind of an idealistic version and maybe a more pragmatic version. And we want it kind of maybe somewhere between that 5k to 10k range. Now, once we've sort of figured out what that k is, then we essentially have a total of 2 to the power k minus 1 models that in theory we could consider, right? So say that we have 10 variables and we want to ask ourselves, okay, if I have 10 variables, how many models are there possible for us to look at? Turns out it's 2 to the power 10 minus 1, which is an awfully big number. Why 2 to the power k? Well, think about it, right? So k is the number of variables. So the 2 is basically just saying for any variable, that variable is either going to be in our model or not in our model, right? If you're counting all the possible models, then we basically could say, okay, well, the first variable is either in our model or not in our model. That's 2 possibilities. And the second variable, that's either in our model or not in our model. So that's 2 possibilities. So that's 2 times 2. And the third variable, well, that's either in our model or not in our model. It's 2 possibilities, so now it's 2 times 2 times 2, and right, we keep repeating that for all k variables. So hopefully the 2 to the power k makes sense. Why minus 1? Well, because if we look at all of those 2 to the power k, one of those is essentially a model that has like no variables at all, and of course we wouldn't fit that model, right? That's not really a model to fit or consider. So that's why we're doing a minus 1. Does that make sense? So we have an awful lot of models to consider. And our goal is, of these 2 to the k minus 1 models, which one of these do we think is the quote best? Oh, look at that, step 1, check. So step 2 is, right, to determine a selection criteria. Selection criteria are statistics that could be generated for each of our models to be used as a measurement of the quality of the model, right? So if I wanted to compare, right, these hundreds of models, well, let's say we have hundreds of models, we pick any 2 of them, and we want to compare these 2 models, right? What's the criteria we're using for our comparison? And in practice, it's good to maybe use a few different criteria. Here's 3 possibilities, so 3 different possible criteria. One is we could compare their R-squareds. That's probably what you would have thought to do right off the bat. We could also compare their MSEs, and we could also look at something referred to as Mallow's CP. And so if I look at that Mallow's CP, that's a new one, right? We know what R-squared is. We know what MSE is, right? The new thing to us is Mallow's CP. If I look at that formula does look a little bit crazy, doesn't it? Does look a little bit crazy. It's got the MSE. So for some variable p less than k is, right, so in this example, k is like the number of variables in our maximum models, right? So maybe that's like 10. And that p is like we're considering a model of some size that has to be less than 10, right? So maybe we're considering a model of 8 variables. So in that case, our p is 8. And our k is 10. So that Mallow's CP is consider the MSE of our 8 variable model over the MSE of our largest possible model, our fullest model, our k variable model. and then multiply that by n minus p, and then subtract n, and then add 2p. The formula looks kind of crazy, doesn't it? The formula looks kind of crazy. But it actually has some intuition in it, and I actually think I described this intuition in a future slide, but I'm not 100% sure. So let's go ahead and talk about it now. The way that this Mallows CP works is essentially you look at the MSE of a 1-variable model, a 2-variable model, a 3-variable model, a 4-variable model. What happens is as you're moving from 1 variable to 2 to 3 to 4, we're building like more thorough models. We're building models with more variables, hence more information. These variables are better at predicting. There's less error. So what we tend to see is as we're adding variables, our MSE tends to shrink. Now, at some point, right, and this is in some way what we're trying to solve. In some way, we're trying to solve for like the optimal value of p. Right, so we have like these k variables, maybe 10 of them, but probably in practice we don't need all 10, right? So that's kind of our question is, okay, I have 10 variables. I probably don't need all 10 of them. How many do I need? Maybe the answer is 5. So in that case, what we would see is we would see the MSE getting smaller as we move from 1 to 2, 2 to 3, 3 to 4, 4 to 5. But if 5 is like the correct number of variables, what we start to see after that point is we start to see the MSE doesn't really change. That is, when you go from 5 to 6, the MSE stays about the same. When you go from 6 to 7, the MSE stays about the same, and so on. So the process of kind of using this Mallows CP is that we keep kind of adding variables. We go from 1 to 2 to 3 to 4, trying to find like where the MSE stops shrinking. And when it stops shrinking, it'll be a roughly equivalent to the MSE of our largest possible model. So when we reach the point, when we find that sort of magic number, that magic p, what's going to happen is that MSE over p, or the MSE of p over MSE of the k variable model, the fullest model, that ratio becomes about 1. And now look at the equation. If that ratio is about 1, what happens to that equation? I have an n minus n that cancels. I have a plus 2p and a minus p, so that becomes p. So if that ratio of MSEs becomes 1, that Mallows CP formula essentially is just p. And so what we're going to see our process is that we're going to keep adding variables to our model. We're going to go from a 1-variable model to a 2-variable model to a 3-variable model, and we're going to look for the point where the Mallows CP is equal to p. And then we're going to stop. Might be worth listening to that slide a little bit, reflecting on it. And of course, right, in the next set of PowerPoints, we'll see this actually applied, and that'll hopefully make it a little bit more transparent what I'm talking about. So, right, the other metrics, multiple R-squared, we know that bigger is better, right? The R-squared is the percent of the variability in Y explained by a regression model. We want a large amount of that variability explained, so we want a large R-squared. R-squared is really easy to understand. It's nice to use when you're communicating with non-statisticians. The downside with R-squared is that it will always increase, technically never decrease, as you add variables to a model. And so if I use R-squared as my lone metric, that is, I say, okay, of all the 2 to the power k minus 1 models, which one has the best R-squared? It's almost always going to be your maximum model. And so in that sense, it's not a very selective process. We don't talk about it in our class because it's not emphasized too much in our textbook. But I think some of you already have like a little bit of an idea that in our output there is something called an adjusted R-squared. The adjusted R-squared kind of gets around that problem. The adjusted R-squared, you can like go to its Wikipedia page and see the formula for it, but it has what's called a penalty process. So normal R-squared, it doesn't really have a penalty when you're adding variables, and because of that, it always picks the largest, most complex model. The adjusted R-squared has a penalty. That is, right, you see more R-squared when you add a variable, but at the same time, the adjusted R-squared formula has a sort of penalty process that at the same time reduces it by a certain amount. That's what's going on there. All right, next one, next metric. The MSE is the estimated error variance of our p-variable model. Right, this is the opposite of R-squared in that smaller is better. Ideally, we want a very small MSE, that mean squared error. We don't like error, so we want that to be as small as possible. Note that the MSE does penalize when we add variables, at least, right, potentially. Do we see that? That's why, remember I said the MSE like shrinks and shrinks and shrinks until it gets to that magic number, and then it kind of roughly stays steady. Because at this point, the amount that it shrinks is offset by this sort of penalty factor that I'm talking about. What's that penalty factor? Well, remember, the MSE is what? The MSE is the SSE divided by n minus k minus 1, right? K is our number. Well, we've been using k as our maximum number of variables, so right, technically it would be n minus p minus 1. Sample size minus the number of variables in our model minus 1. So it is true, kind of like R-squared, SSE will always decrease. The numerator, the SSE, always decreases as I'm adding variables. But when I'm looking at the MSE, that denominator, the n minus the number of variables minus 1, as I'm adding more variables, I'm subtracting a larger number. The denominator is also getting smaller, right? So for the MSE, as I'm adding a variable, the numerator is getting smaller. That's making the overall quantity smaller, but the denominator is also getting smaller. And that's making the overall quantity larger. And at some point, those two kind of start canceling or balancing one another out. And that's kind of the idea about how we kind of figure out like the optimal number p. So malloc-CP, I talked about that a little bit in some of the previous slides. Malloc-CP is referred to as a measurement of the mean squared prediction error. And like I talked about, it's roughly equal to p. I showed this in the equation. It's roughly equal to p when the MSE of our p variable model is equal to the MSE of the k variable model. And that's basically implying that the correct model is of size p. If our p is too small, what we see is an upward bias, and our CP is more than p. We'll look at this a little more closely with a concrete example in the next set of PowerPoints, which will hopefully make it a little bit more easier to understand. Oh, here I just pulled that formula up again so we could look at kind of how when that ratio is 1, which means that the numerator is roughly the same as the denominator, then like the other part just simplifies to p. We talked about that already. So in practice, this is what we suggest doing. In practice, we can let p get gradually larger and larger and larger. We look at all the one variable models, that's p equals 1. Then we look at all the 2 variable models, that's p equals 2. Then all the 3 variable models, that's p equals 3. Right? We keep increasing that p. until we finally find the point where that CP is less than or equal to P. When we find the point where the mallow CP is less than or equal to P, the first time we hit that point, boom, that's our optimal number P. So that tells us, say that happens at like P equals 3, then that's basically saying our optimal model is a 3-variable model. Once we've made that decision, we could use some secondary criteria like R-squared or MSE to say, okay, of all the 3-variable models, which one do I think is the best? All right, so that's one possible approach to picking our best model. All right, so we talked about criteria, and also a little bit we talked about approaches. Here we're going to talk about approaches more explicitly. We're actually going to talk about 4 different very common strategies for selecting your variables. The first one is the all possible model approach. The second one is called forward selection. The third one's called backwards elimination. And then the fourth one's kind of a blend of 2 and 3. It's referred to as stepwise forward selection. So we're going to talk about, again, big picture, what each of these 4 are. I know this is like it's a lot of abstraction to have thrown at us. I do promise the second set of PowerPoints is all working through this in the context of an actual example, and I think that'll really kind of hammer home what we're talking about right now. So just hang in there. Now, a few things to keep in mind, right? Like selection criteria, it's often preferable to use a few different strategies. So we'll talk about that when we do the examples. Also, the last 3 of those strategies, the forwards, the backwards, the stepwise, those 3 strategies execute an algorithm that is p-value dependent. Since it's p-value dependent, we need some sort of alpha level. We need something to compare our p-values to. And so, right, if we want the most reliable prediction of future observations, we might use a liberal alpha level. So we might use an alpha level of like 0.10 or 0.15. If we want the simplest, the smallest model possible, we might use a very stringent alpha level, like 0.01. We'll talk more about that when we do some examples. All right, so let's talk through each of these 4 strategies. So strategy 1, all possible models. This is almost like the brute force approach, although we're really letting SAS do all the brute forcing. This essentially asks SAS to generate all of those 2 to the power k minus 1 models. Very thorough, right? But of course, even in this like modern day age, 2 to the power k can get fast quick. Try putting 2 to the power 1,000 in your calculator. It's not going to look pretty. So at some point, the k will get too large for us to do this. But when our k is not too large, this is a very nice selection strategy. And how it basically works, we'll see in the next set of PowerPoints. It's really that mallow CP process that I described before, where we look at all the 1-variable models and compare that 1 to the mallow CP. Then all the 2-variable models, we look at mallow CP and compare it to 2. We look for the point where the CP equals P. All right, that tells us the optimal P. And then once we find the optimal P, we look at all the models of that size and like find the best one, say with the best R-squared. So that's actually the kind of how the all possible model approach will work. All right, selection strategy 2, forward selection. We've actually talked about this already. Like we've sort of foreshadowed this approach. We've talked about it. Actually, I think we talked about it in the partial F lecture. And I think we've actually kind of played around with this approach in labs. So 1, right, here's where I was talking about you have to choose this alpha level for inclusion. So, right, maybe you're going to use the usual 0.05, But if you want to be liberal, you might do something larger. If you want to be stringent, you might do something smaller. And what you're going to basically do, you're going to select the predictor that's most highly correlated with Y. If its f-test is not significant, then you stop. If our best variable is not significant, none of our variables are significant, there's nothing going on. However, if it is significant, we add it to our model, and we go to the next step. Now we fit all two variable models containing x1 and all other variables. We determine the significance of the second variable based on its partial f-test. So we're essentially finding the variable of all the remaining variables, which one adds the most above and beyond x1. If that variable is significant, add it to our model. Then we look at all three variable models. We say, okay, of all the remaining variables, which one adds the most above and beyond, right, x1, x2? Put that in our model, and we just keep going. We keep adding variables, right, this forward building process until none of the remaining variables are significant. Right? The backwards, so that forward elimination is our constructive approach. We're building our model, right? The backwards elimination is the destructive approach. We're starting with the largest model and we're whittling it down. We're making it smaller and smaller and smaller and smaller. Again, we need to specify a significance level. We start with the largest possible model, our maximum model. We look at all those variables and we look at their partial f-test, right? The type 3 sum of squares f-test, and we say, of all these k variables, which one adds the least above and beyond the other variables? Assuming that its p-value is non-significant, we remove it from our model, and then we rerun the model. So now maybe we've gone from a 10 variable model to a 9 variable model. Now with our 9 variable model, we look at all those type 3 sum of squared p-values. Which one of these 9 variables adds the least above and beyond the other 8? Assuming that's not significant, get rid of it. And get rid of it, and get rid of it, and get rid of it. You're always looking at the type 3 sums of squares, finding the largest p-value, the variable that has the largest p-value, and removing it. And then rerun the model. Find the largest p-value, remove it. Run the model. Find the largest p-value, remove it. Keep doing this until all of the p-values are less than your specified alpha level, your specified significance level. And then finally, right, our step 4. Our step 4, the stepwise forward selection, it works the same as forward selection, except a variable selected into the model can later be removed if its significance level falls below a pre-specified level. So, right, when would that happen? Right, it might be that, like, right, we add our first best variable, and so the variable that's better than any other variable, that goes into our model. And all that's saying is that if I had to build a one variable model, this is the best one. But as we add more and more and more variables, it might be that, right, there's a collection of like 2 or 3 variables, any one of which is not as good as the first variable we started with, but the 2 or 3 of them collectively make that first one redundant. And the stepwise forward selection allows us to at some point detect that, right? We add the first variable, that's the best one. We add the second, the third, and the fourth, and then it turns out that the second, third, and fourth variable make that first one redundant. The stepwise forward selection has this extra process that detects that that first variable we added is redundant now and removes it from the model. So it's like a combination of adding and removing variables. So kind of a blend of forward and backwards. So there's 4 approaches. Again, which should we use? Like I said, all possible models, because of how thorough it is a great strategy when possible. Otherwise, it becomes like a little bit of a matter of personal preference, right? For me, like I guess I have a destructive personality. I like the backwards approach. It feels nice and intuitive to me, but to other people, the forward approach feels more intuitive. It's not right or wrong. It's a little bit of a personal preference. Regardless, be critical of whatever strategy is employed. There's a lot of articles, there's a lot of papers, right, that warn against using automated processes like this because, right, there's lots of examples in where automation overrides common sense, right? These computers, these algorithms lack the common sense that we as statisticians have. And just one example of this is they often will do things like include higher order terms, like an x cubed term, without lower order terms, which, right, we know from our previous PowerPoint, the polynomial PowerPoint, we don't typically do that. And then again, a reminder, once we determine our final model, we are not done, right? Once we've like figured out, okay, this is like my best model, that's like in some ways just the beginning, because now I have to look for outliers. Now I have to test my assumptions. Now I have to test for collinearity, right? I always need to keep those diagnostics in mind. All right. When do we talk about cake? All these narrations are starting to blur together. Regardless, I'm gonna go get some cake. And I invite you to join me. And after we're done, let's maybe get a nice glass of milk and reconvene.